Okay, so I'm going to explain a little bit about how I've made the simulation to investigate how this embedding algorithm combined with the evolution of the system has some compatibility with Newton's laws. Now this is obviously preliminary evidence and I'll need to do further checks, but obviously it's just to get some interest in the system, and maybe with some collaboration we'll be able to get a little bit more deeper here. But like I said before, I can perform I can start off with a union state, which is essentially just a very, very simple state graph of n point particles, where every connection between each point particle is just one space element in size. Then from that union state you can perform one single microstate path, and this one single microstate path could be, I don't know, like 1,000 time steps. Okay, and as you do that, you get to some final state that's a little bit more complicated, you know, something like this, but it's still, we're keeping the number of point particles constant, and so now we will have interaction edges with various information on them, and this is imagining the system not, you know, embedded within a coordinate space yet. So once we get this final state, what we do is we input it into our other into multiple as the input state for multiple microstate runs. So from there you'll get another state which will give you some other state, and you go here, give you another state. In fact, it'll give you a series of other states, and you know, this could be up for another 100 time steps, let's say. And you may do this, you know, this could be 100 loops, let's say. So we can do this once, but the results that we're going to get when we average the values here, let's say we're interested in some expectation value, right? Well, let's imagine that we're looking at these sort of 100 time steps. Well, what's going to happen is we're going to have, let's say we're looking at 1 point particle. It's going to be in a given state that's specific for each time step, but then there could be a multitude of different sort of zigzaggings that it may do. It may kind of go here and then here and then here, and then there's a let's say we're going just for like 1, 2, 3, 4, 5 time steps, and there'll be another evolution where it'll go here, then here, then here, then here, then here, another one here, and then here, and then here, and then here, and then here, let's say. Right, each of these, there's 3 different evolutions, right? And what we might do is we might say, okay, well, what's the average position at the end of all of this? Because what's really happening is we're going to have an initial state, and it's going to evolve, and then it's going to end up with basically like a cloud of possible states, like you saw in the last video. And what we could do then is we can just say, okay, let's take all of these states and let's just average them. Let's find out an expectation position. Okay, and this would be the final expectation position of all of this cloud of states. Now, what we're doing with the proving Newton's laws, or like showing that there's some compatibility with Newton's laws, is we're running the system with all of the actions updating the system, but at one point we suddenly stop the update. Now the reasoning behind this is that when actions reach the centralized point particle and update the system, that is in effect applying a force on the system. That's the suggestion there, because when you apply a force on the system, when an action wavefront reaches the centralized point particle, it tells the centralized point particle I mean, let me just do this for example here. Let's say we've got a simple system. Okay, here's another point particle. Here's another point particle, and we've got the interaction edges between them. Let's say a duplication occurs here, and it propagates through the system, reaches one of the point particles, and then propagates through the system here, and eventually reaches the centralized point particle here. Let's call this P0, this is P1, this is P2, right? And over some time, this action wavefront eventually, like we saw in the propagating information propagating system of the interaction edge in the last videos, eventually it gets to this point particle and it updates it. Well, what that does is it changes what this point particle thinks is the distance between point particle 1 and point particle 2. Now that's going to affect the velocity, right? The velocity is determined at each time step by the strain on that particle at that point. Now, if you increase the size here, that's going to have the effect of either increasing or decreasing the strain. Right? If you increase or decrease the strain, you're going to have a change in the resultant velocity. And so that's why there's this comparison between actions updating and the motion of the system. So this is I can for the microstate I can actually make a mathematical argument for this, which I'm not going to do right now, but at the moment I just want to show you sort of my thought process. Okay, so I think it would be best if I just show you sort of the process that I went through when trying to do this. So going back to our example, what we're basically doing is we're running multiple initial time steps, and then we're doing multiple evolutions, and then we're going to take this difference between the initial position and the final expectation value, and we're going to average. We're not going to average, sorry, we're going to divide that by the time difference. So let's say this is delta x, right? If we want to work out the velocity at that point, we're going to do delta x divided by the time difference. And that gives us the average velocity between the initial state and the final state. And like what's really happening is all these things are going on weird paths like this that lead them to their final states. So you have something like that. Like that. And obviously if you were to take the incremental velocities, these might actually be quite high, right? Because you might have something that goes like that, boom, like that, and then goes back down there. But on average, it's still less, right? So this is important because when I do this simulation, this has an impact on the energy conservation of the system. So we take this and we work out what the velocity is, but then at this point, after this point, for every single state, every single microstate, we just stop it updating, right? We just, whatever the matrix is, the state matrix for the graph at this point, we just allow it to stop updating, and it will just continue with the same state, right, without there being any dynamics on it. And this is supposed to represent the absence of force on each at that point of that point particle in each microstate path. If that kind of makes sense. So to maybe I could draw this a little bit better. So we've got an initial union state, right? Because we need to have some state to start with. Then from that we have multiple state runs. Okay, multiple state runs. And these are going to give multiple initial configurations or initial inputs for our system. And this is important because if I just run from the union start, then I'm not going to have any interesting dynamics in my system. No complexity has evolved out of the system yet. It's this act of collapsing into a specific state of the system that enforces the system to behave in a particular way, right? And this is what I think leads to in the future, as we do many time steps, the sort of phase transition into situations where you have forces breaking away and sort of stable particles forming. So these measurements of specific microstates that then leave a memory, in a sense, on the system. So we've got a union start, and it leads to multiple input states. And then these input states then do multiple loops. So you'll have multiple loops coming off each one of these. Okay. And like I said, for each of these multiple loops at the end, you work out the expectation value of the position for each one of these, and that will give you the expectation change in velocity, essentially. And then each of these states are then allowed to evolve a certain number of time steps, but without any actions happening. So essentially, the system is frozen. The state of the system is frozen and then allowed to evolve via the time iteration evolution algorithm. Yeah, that's basically what it is. And we're seeing what we're measuring along this part, right? So we're measuring the first bit here. This will be TS. Well, this is, let's say, if this is it, we say this is TS1, this is TS2, and this is TS3, right? So this is how many time steps we have before our first iteration, then we have time steps before we relax the state, and then how many time steps are we relaxing the state for. And we're measuring the velocity, and we're also measuring the acceleration. So let me show you a little bit about of what I've done. So I'm going to take you through the process of me doing this. So when I first created these simulations, I actually just did them from one microstate. So I'd evolve a microstate. Here you can see from union start. So we're just doing one here. We're just doing one. And then once we get our final state, we add the final state no force time as many times. So that's like the TS3. This is TS1. Right. So this was actually, we started off here actually doing it from union start. So we didn't actually start off with this. So it's almost as though the first exploration into this, we just did. Can I change the colors here? I don't think, can I? We just looked at this bit. The first bit we sort of just looked at one of these, right? And then we sort of included the union start, and then we did all of them to look at how it acted overall in the system. So this is where we're just doing it with one microstate. And we looked at it, we get something like this. And we apply it a bunch of different times. Obviously, this is a non-deterministic system. When I say non-deterministic, I mean it's based on probabilities as it evolves. And you get all of these weird shapes. So this is actually measured from when it's relaxed. The yellow line is the acceleration. You see the acceleration drops down very quickly, and we do get this nice, what looks like almost constant velocity, but then of course we've got all of these other weird shapes going on here. Some of them drop down to zero straight away. Some of them bump up a bit. These are because we're literally looking at individual microstates doing this now. We're looking at individual microstate paths relaxing. We're not looking at an ensemble of microstate paths. So the idea is we take all of these for the final states, and then we average them over an ensemble, or we average them over a collection of microstate paths, or loops, if you do a Monte Carlo simulation and then run it over them. And so we do. So if we do that, we get something that looks a little bit more like this. Obviously, we're not doing that many time steps yet. Okay, and then Okay, so now we updated a little bit more. Now this time we start doing the same sort of thing, and still it looks like it's sort of dropping down quite low values here, but it's still kind of it's giving some some linearity here. But this is where I realized actually I was using the wrong algorithm. I could have used an algorithm that was much faster. And so when I started using the faster algorithm, that worked a lot better. So if we just go down here, we should get to there, hopefully, if I haven't deleted it all. So I haven't deleted it. Okay, here we go. So this is where we averaged it. We started averaging it, and we did a number of iterations for this now. So this is where we start including multiple initial microstate runs. So this is where we start including the whole picture instead of just one microstate run. So this is the reason behind why we were getting such weird answers before. It was because each one of these graphs we had done only one microstate run, and then we input the result of that microstate run as the input for the Monte Carlo loop. And so any sort of weird behavior you get here is kind of characteristic of the input that we put in from the initial microstate run. You've got a very specific state that you're using as your initial condition. So the initial conditions were what kept these looking kind of weird, right? So I then use it over iterations, and then now you can see something a little bit nicer looking here, right? So we've got the velocities. So this is just after we've done a number of microstate runs, right? And we're averaging the velocities. And we average the velocities firstly for 20 time steps, and then at 20 time steps, we then suddenly relax the system for 80 time steps, and we see this decay, right? Now, look, the acceleration drops down to something almost like 0, which is good. That's what we want. That looks like it's beginning to behave similar to Newton's first law. And also the velocity, obviously, naturally, if the acceleration is going to 0, the velocity goes to being a constant value. So that looks nice as well. However, it looks as though we've got this quite large energy gap here, right? Where suddenly the velocities are really high, and then suddenly we go to like a really low velocity. And this is because, like I said before, when we're looking at this system, when we're looking at this system, everything kind of moves in lots of different directions. It's jiggly-jaggedy. It's almost Brownian motion-like in the way in which these particles might move, and so they might, because of the randomness of the evolution of the state graph, may move in multiple places, and these are the instantaneous velocities that are large, right? So the instantaneous velocities, the energy is quite high. But if you take this and you time average it, so that means you take the average expectation value at the end, and you take that to be the delta x, and then you divide that by the change in time for that to happen, then you get something which looks a lot more like energy conservation. So this is here, you can see it's tending towards constant value, which looks nice, but I had to update the code. So I did this one for the first time, and it kind of was quite high. I think that was because I only used a very small number of time steps here. So you see, like I only did it for like 20 time steps, and it makes sense that, you know, if you're talking, the smaller the time difference, the higher the energy is going to be, right? Because you're trying to time average the energy, right? The smaller the increment, the greater the more erratic the velocities are, but they average out as you time average them, and so there is a point where you start averaging these times out, and the time actually drops down. You see here the time drops down to something much more to what the velocities are. Obviously, we still have some slightly weird jumping up and down. I think that's because I didn't quite do enough iterations, but it's much closer to the value. So this is the value from the initial position to the final expectation position, right? The average initial position to the final average. So what we've done here is we've taken the average, we've taken the expectation, we've taken the initial position, and we've subtracted that from the final expectation position, and then we've averaged over the iterations that we've done, right, for each of the initial microstate runs. And this is what we get. It tends to be quite close. Now this one's dropped down a little bit below, and I think because as you increase the number of time steps, like I was saying before, the more time steps you have and the less iterations you have, the system's going to increase in its error, because because you have a smaller sample of the overall Hilbert space. I think that's the correct phrasing, or the overall state space. Right, the space of possible states. You're reducing the sample size for the more time steps that you do. Right, if you just do 2 time steps, there's going to be way less states that you can occupy for that evolution. Whereas if you do 100 steps, it's going to be way more. So we keep doing this, and we look at some more, and it does tend to seem to be around these values, but I'm not really investigating it in any real depth. It's only really in the next investigation where you can begin to see. I also looked at the average time and then the average relaxation time as well, and you can see it does seem to tend towards getting closer towards that value. But what I did do is I think this is the best. So you can see it does at some point get smaller and smaller and smaller, and begin to tend towards that value. The difference gets smaller and smaller. But I think the best evidence lies. I think I did one simulation that ran overnight. Oh, this one's nice. Okay, so here you can see it's a gradual increase. We're doing a gradual increase of only about 2 time steps for each iteration. So initially we're only looking at two time steps, then we relax and we do another 2. 2 time steps, and then we relax for 2. Okay, so at first the energy is a bit higher than that, but as we increase the time iteration, as we increase the time difference, this value tends to drop down closer and closer and closer to the velocity that the particle relaxes at, and you can see it gets really close here, right? Very, very close to this true value. And obviously, you know, the further out you go, the greater the accuracy. But then I plotted this graph, which really does show that it seems to tend towards that value. Obviously, as you get further time steps, theoretically that would increase the uncertainty a little bit. But it definitely looks like the value of the average velocity that the particles are moving at tends to be the same as the velocity when the system is fully relaxed and doesn't experience any incident actions. So I mean that's kind of evidence for Newton's first law. So the system has a certain amount of energy corresponding to the average locations of the initial and final positions of the particles, and you can average that over a certain number of loops. But what happens when you change the system and add an extra particle in, or not particle, add an extra action wavefronts? Let's say there's no action wavefronts hitting the centralized point particle for a while, right? Which is very unrealistic, I would say, but we're using it to really investigate this idea of there being no force acting on the system, and what happens to the system when there's no force acting on the system. Okay, so it relaxes and we get this nice sort of relaxation phase. By the way, this sharp spike at the beginning, I'm pretty sure is to do with the jump from instantaneous velocities to this sort of relaxed velocity that goes to a constant value. So the instantaneous velocity is you imagine the whole system is jumping about, and we've taken all of these velocities to just be average to the average velocity, to be equal to the average velocity. So it's natural that there's this jump at the beginning. But notice that these velocities are all below 1, quite nicely below 1, which I'm pretty sure is the upper limit over a given time. So if you have a certain amount of time, it's a very small amount of time, that will be the upper limit. Okay, so the next thing that we're doing is we're basically applying an excitation while the system is in a relaxed state. So this is the sort of thing, and we're looking at what effect that has. So an excitation would just be the system is relaxed in the sense that the state matrix that describes the effective interaction edge length, or the effective number of space elements in each interaction edge, is constant over time. That's why we're getting that relaxed pattern. But then we add some value, some number. Let's say that a single action wavefront comes along, a bunch of duplications happen all at once, or a bunch of reductions happen all at once, and then there's just one. You remember at the beginning when we were looking at those, looking at the evolution of the interaction edge, you get those almost like photons that appear. Imagine one of these comes along. Okay, so what would that do? That would update the edge weight of one of the interaction edges. So that's essentially what we're doing here. We're changing it so that now we update the edge weight with 20. Okay, we're just going to add 20 to it, and I mean we're looking at edge weights of around about 10 to 20. So we're basically doubling an edge weight, maybe tripling it. And you can see you get this kind of behavior. Now this is what's really interesting. You add, when it gets that value, the new velocity that it seems to be relaxing at seems to be at a higher constant velocity. Now there seems to be some jumping up and down here, which also, and there's a non-zero acceleration. The reason, so first of all, the velocity goes to another higher level velocity. So I think that may very well relate again to energy conservation. That you have a photon updates the system, and then that is transferred in some way to the momentum of the particle. The fact that we're getting a non-zero acceleration here implies, because it looks pretty constant, this velocity, it implies that we're getting some change in direction. And I would argue, if we look back at some of the other simulations, this is a result of the fact that our state is not scaled to a large size. So if you have a small state, you have a small matrix or a state graph, and then you excite it by adding double that size, then you're going to end up with this effect where the particle is going to be pulled back into where the other point particles are. So I believe that at much larger time steps, this acceleration will actually go to zero. This acceleration is to do with the fact that the particle's being pushed to the outside of the state graph, and it's being pulled back in by the other point particles. So I think that this will not happen at larger time differences. Anyway, so this is some evidence that I've got, and I think it's quite interesting, really. The idea is that particles are made up of lots and lots of point particles. The interaction edges between them reduce a little bit more than they duplicate, and so this has the effect of creating these stable states, which I outlined in my first paper. And what I'm looking at now is how many branches there are inside these clusters and how much information is stored within them, and whether there's any way of sort of connecting that with E is equal to mt squared, possibly. And the other thing is gravity, obviously. I have this feeling that when you have a cluster, it increases the amount of tension or strain, sorry, in the region around it, which has the effect of, when particles come close, pulling them in. Now, if we relax the state of the system, we keep relaxing the state of the system, eventually the system comes to a halt, right? It does seem as though this violates energy conservation. But then at the same time, where does energy come from, right? We've got these duplications and reductions occurring between point particles, and that gives energy to the system. But that energy doesn't come from anywhere, right? It's just sort of innate thing that happens, right? So I would hypothesize that energy conservation is a rule that works for the energy for the scales of our own universe right now. It's almost as though things have balanced out. So if you were to imagine that no actions affected a centralized point particle, no action wavefronts came onto a centralized point particle, then the system, via the time iterated embedding, would eventually go to zero velocity, would eventually relax to zero velocity. I mean, you do sometimes get these oscillation patterns that happen, but that's really to do with the fact that we're limiting the amount of decimal places that we're working with, and so it creates a sort of a loop pattern. But really, if we're working with a continuum background, or for the embedding, then it does relax to a final state, or at least almost, pretty much. So it's such a tiny movement that it would be basically nothing. The idea is that the fact that energy comes out of the space elements just naturally cancels out with that fact that if you just let the universe relax without any incident energy, it would just go to zero energy eventually. So anyway, I think I'm going to end the video there, but I'm really interested in knowing what anybody who's listening to this video thinks about the results that I've got. And so I think I'm at the point where I'm able to give some proof of or some evidence of Newton's first law being satisfied by this system. Newton's second law also comes quite neatly out of the fact that Newton's first law applies to the point particle, and if you have a cluster of point particles, they're made up of lots of point particles. The mass of that, the inertia that cluster of point particles feels, is directly proportional. Also, in the inertia that it feels is directly proportional to the mass, and the more point particles there are, the less a given amount of action that's incident on it is going to actually cause it to move. So that naturally comes out of that fact. The third law comes from the fact that when an action or propagation, an action occurs, it propagates through the interaction edge in both directions. And as long as the system is not evolving faster than the speed of light, right, and that is the case so long as the rate of duplication is not greater than the rate of reduction. So long as the rate of duplication is not greater than the rate of reduction in the interaction edges, then the propagating duplications, the propagating reductions will always eventually come and update the system. So you can think of every action's reaction as being the action wavefront going in the opposite direction. And so it will go to the other. So if a particle, let's say particle P1, acts on particle P2 with a force, then particle P1 it will create an action that will go past both of those 2 point particles, and one will be updated on the other point particle, whereas the other one eventually, when it reaches that information reaches the centralized point particle, it will update on the other, and so it will push back. So I think that's the idea for Newton's third law. But these things, this is just my hunch, really. I mean, I haven't quite formalized this yet, but I wanted to give this as an introduction. Well, not an introduction, as a demonstration of the sort of things that I'm doing. I've got various different simulations that I've got. I'm also looking into forces, how forces evolve out of this, and I've got a number of different, strong electric weak phase transition, trying to look at that, investigating distributions, defining okay, I was trying to define the SERD model within the Wolfram Physics Project model. Visualizations, I've got these visualizations which I've only shown you. I've got some tests, but this is not most of it. Most of it is down here. One of the big things that I'm doing at the moment is looking at, as well as making nice visualizations of the system and things like this, looking at how the velocities of the wave fronts, action wave fronts, is constrained to be 1 on average. And that's something that I'm investigating even further, which I seem to be getting pretty positive results from. Anyway, I'm going to end this here. Let me know. Do contact me if you are interested in the research that I'm doing, or if you have any questions. I would be very interested to hear from you to hopefully discuss this in a little bit more detail. I do know that it has quite a lot of similarities to the Wolfram Physics Project and the Wolfram model. However, I do think there are some differences in the way that I'm viewing this system and the way that they are in the Wolfram model. That's not to say that there isn't some amazing results that have come out of that. It's just difficult for me to implement this system within that model. But maybe I can get some help with that.